All right. Hello, everybody. Welcome. Happy Monday. Here we are back again, ready to do some more physics. So we'll give everyone a minute to jump on. As we do, a couple of reminders as always. First, my name is Sam, and I am super excited to be here with you as we head towards the AP test. I know it's coming, a couple more weeks. Today, we're talking about oscillations, so we'll get started in just a moment. If you would like to play along with me today, we will do some practice problems, so grab some scratch paper, a pencil, maybe a calculator, and we'll get started in just a moment. Ooh, Kristen is here in the chat. Welcome, Kristen. Kristen is our wonderful Physics C Mechanics TA. She is here to answer any and all of your questions. So welcome. Hey, Casey. Welcome back. If you have questions as we go, I'm happy to answer it, but also Kristen is just as an expert as I am. So she is going to do her best to answer questions in the chat as we get going, just to make sure that we can get through everything. Hi, welcome, Gregor. So let's get started. So like I said, today we're talking about oscillations. First things, as always, kind of the standard logistics at the beginning. We are recording this, so your name or any of the questions that you ask might appear on the website, YouTube, etc. So just be aware of that, and if you don't want your real name, go ahead and change it. And as always, plug to follow us on social media. So if you're not yet following at ThinkFiveable on Twitter, Instagram, YouTube, we are here and happy to help especially as we continue to approach the AP tests. I know they're coming, and so everything's kind of ramping up. So we are here to help you get through these next few weeks and hopefully do well. So with that, in the stream, like I said, we're talking about Unit 6, which is oscillations. So there's 3 big topics. The first thing, we're going to just generally talk about simple harmonic motion, what it is, and kind of the different types of things that you'll see, and just a couple of kind of extra. There's nothing really super brand new. There's just kind of some extra things to throw at you when we talk about things that are in simple harmonic motion. And then we are going to dive into kind of the two big types, mass on a spring and pendulums. So again, as we're here, if you've got questions at any point, I'm just going to keep saying it. Definitely throw them in the chat. We are here for you, here and happy to help with whatever we can. Great. So let's dive in. So first, let's talk about simple harmonic motion generally. So that's going to be, when you see the word simple harmonic motion, there's going to be some special characteristics of this motion that we can talk about. So it should kind of cue you to switch your brain into these extra special characteristics that we'll talk about in this first section. And the first thing we'll talk about is the actual motion variables. So we'll talk about position, velocity, acceleration, and then we'll talk about some new ideas called period and frequency and how we deal with those. So first, what is it? There's really 3 kind of big types that you'll see. The first one is uniform circular motion. So if you have not checked out the Cram, it was like, I think 2 Crams ago, on rotation and uniform circular motion, there's a lot more info there, but we are going to hit the big ideas that relate to this idea of simple harmonic motion today again. So the first one is uniform circular motion. The second one is mass on a spring. So you can see we've got a block here. That's kind of mass is kind of the general term. It's usually a block. Sometimes it's other stuff. And it's oscillating on this spring. So it's going up and down in this kind of repetitive periodic motion. And then the last one is the pendulum. So we've talked about pendulums in terms of energy before. We'll talk about them again today with some more specifics. And we can see here that all 3 of these motions are making this wave pattern. So hopefully we see that we're going to maybe be talking about some sines and cosines today as we look through this wave pattern that each of these 3 motions are creating. So kind of the more technical side of it, the more mathy side, there's a kind of a general formula for simple harmonic motion. and it's written here. So this is not on your equation sheet, and this is something you definitely should memorize. So if we dig into it just briefly, we can see that the general formula for simple harmonic motion, it's the second derivative of x with respect to t. Remember that that's a different way to write acceleration, right? So we're taking the acceleration of the motion, we're adding it to this new variable called the angular frequency. It's omega, and it's omega squared times x. So it happens. So simple harmonic motion happens when you've got the second derivative of x and x in the same formula, and you can see it equals 0. So this is kind of something you're going to want to memorize, because you're going to see things written like this, and you'll need to be able to pull out, like, this is the angular frequency of the motion, because that will help us to help us analyze the motion. So this is an important formula. It's not on your equation sheet. They do give you the solution to the differential equation on your equation sheet, and that's what this is. And we'll dig into that in a second. But the actual general formula of simple harmonic motion is not on your equation sheet. So you should probably memorize it, unfortunately. Sorry, guys. Okay, so for the solution to the equation, so if we look at it, there's a couple of key things to pull out here. Like I said, this is on your equation sheet, and the two really big ones we see in my box on the bottom right here. The first one is this x max. Sometimes you'll see it written x max, sometimes you'll see it written a. Regardless, we call it the amplitude, and all it is it's the maximum value away from 0 in this sine cosine function. So if we look kind of generally here, you can see that the motion goes, up and down, and it will vary, but the amplitude, this plus a or minus a, is the max value away from 0 of the motion. And then the angular frequency, we symbolize it with an omega. And this is something that is a new idea, and we measure it in radians per second. And if we're talking about it in terms of uniform circular motion, it works the same way as the angular velocity. So those are interchangeable. You can use either one. So how do we actually work with these equations or these functions? The way that we do it is just like we would work with any other displacement, velocity, acceleration function in physics, where when we've got a position function, which is the one that I gave you, if we want to take a derivative, we'll take a derivative of it to get the velocity function, and then take another derivative to get that's a typo, that should say acceleration, to get the acceleration function. So we go, we take a derivative, we take a second derivative to get the acceleration function. This, the actual function itself is correct, but I forgot to change the velocity, and this should be a. So I'll update that in the slides for you so that you have them in your resources. But the kind of the general takeaway here is we just take derivatives just like you would for any other displacement, velocity, acceleration function. It just is a little funkier because we have to remember how to take the derivative of a cosine function or a sine function. The short version, remember that taking a derivative of a cosine function, you get a negative sine function. And don't forget to take the derivative of the inside. I think it's the chain rule. I think that's the math name for it. And then to take the derivative of a negative sine function, you get a negative cosine function. It also works in the other way. If you want to go from acceleration to velocity, you would integrate. Velocity to position, you would also integrate. Okay, so just a couple of quick reminders. Oh yeah, Kristen's throwing a bunch of stuff in. That's awesome. Sorry, a couple of quick reminders about uniform circular motion. So these are from the other Cram, but they apply here too. So in uniform circular motion, which is one specific type of simple harmonic motion, we remember that the speed is constant, but the velocity is not, because the direction of the motion is constantly changing. We remember that there's always a net force, and the vector points towards the center of the circle, and there is always an acceleration because that velocity vector is changing. And then here we go with this. With uniform circular motion, remember that we've got two extra values that we can look at. We can look at the centripetal acceleration, and it's v squared over r. This omega here functions the same way as the angular frequency. So if we pull omega out of one of the simple harmonic motion functions, either the cosine or that initial, d second derivative of x with respect to time function, the general form. The omega functions the same way, and they're interchangeable. And then centripetal force as well. Okay, here we go. First practice problem. So we've got a particle. It moves in a circle in such a way that the x and y coordinates of its motion, given in meters as a function of time, are 5 cosine 3t and 5 sine 3t. What's the radius of the circle? So I am going to give you a second, and if you're working on it already, great. If you haven't yet, or if you're kind of like, I don't even know where to start with this, you are not alone. The trick here is to recognize that these x and y functions are really the simple harmonic motion equation. So if we take a look at this, we know as a rule that the number in front of the cosine is going to be your amplitude, and then the number before the t is going to be your angular frequency. So in this case, because we're looking at it says it's particles moving in a circle, we're looking at uniform circular motion. The amplitude is going to be the radius. So this is actually a pretty straightforward problem. We're looking to find the amplitude in either of these equations, and then know that the amplitude is the radius. So I'm going to open up a poll, and let's see what we can do with this. I'll give you just a couple seconds, because I did kind of give you a place to start with this one. And see if we can't find the radius of the motion, or the circle, radius of the circle. Take another 15 seconds or so. Great. So if you're voting, last chance. We've got a lot of votes in. Cool. Okay, here's what we have. Great. Y'all got it. Absolutely. So it's just C, right? So if we take a look at this one, I will always structure my problems in a way that maybe is helpful for you too. I always think first about, like, what does the problem tell us? What do we know? What relationships are going to be helpful to us as we try and figure out the answer and then solve it. So things we know the two functions, we know what's going in a circle. The relationship that's helpful for us this time is the simple harmonic motion solution. And then again, because it's going in a circle, the amplitude of the motion is going to be the radius. So you can see it's 5 for both, right? That's on purpose because, the max x direction and the max y direction is going to be 5. And so we can just pull 5 out of that equation and get that as our radius. Let's do another one. So here we go. Particle moves in a circle again. And again, it's the same kind of setup, right? The functions are the same, but now the question is, which of the following is true of the speed of the particle? So this is going to harken back a little bit to uniform circular motion. So remember that we can use the omega in the simple harmonic motion equation, just like we would use angular velocity. And that should help you to find the speed. So let me see if we can try and answer that one. Poll is open. Take a minute. I know this one's a little bit more of a stretch because it's going to ask you to think more about some of the things from uniform circular motion. I didn't explicitly cover it, but I want to see what y'all can do. Take like 30 seconds or so. Great. Okay, if you're going to vote, do it now. Last chance. Cool. Okay. So we're a little bit more split on this one. So let's definitely talk about it. So the correct answer here was B, and we should definitely talk about why. So if we take a look, it looks like we were between B and D, which is good that we recognize that we definitely need that 15 in there, right? So the way we figure this out is we remember that we can relate the linear speed of the particle to the angular velocity, angular speed, with this V equals R times omega equation. So easiest way to do this one is to just pull out the 3 from the original equations as your angular velocity, and then relate it to the linear velocity by multiplying by the radius. If we think about this also, just remembering our uniform circular motion rules, the particle in uniform circular motion will always move with the same speed. The only thing that's changing is the direction of that motion, right? So if we're moving in a circle, the speed of the object will always be the same. So right away, we should be able to rule out C, D, and E, and then just figure out if it's A or B. That will be different for mass on the spring, which we'll talk about in a second. Okay, last one here. So we have a new function now. Particle moves in the xy plane, coordinates given by, and you can see the general formulas. A is 1.5, omega is 2 radians per second. Now it's asking for the magnitude of the particle's acceleration. So remember, you can either take a derivative, or all of your uniform circular motion rules apply. So if you were to find the acceleration using the uniform circular motion equations like that guy, that would be totally legit. Let me get you back there. Take about 30 seconds. I'm going to open up another poll. Take another 10 seconds or so. Okay, last chance if you're going to vote. Now's the time. Great. Okay, so let's take a look at this one. The correct answer here was E, and some of us got it, which is great, but I do want to take a second for those that didn't get it. Here we go. So again, the first thing is we see that it's moving, particles moving in the xy plane, and we see these simple harmonic motion cosine sine functions, which tells us uniform circular motion. From there, my brain is like, cosine and sine are kind of confusing sometimes. I'm going to try and stay away from them as much as I can and just use my uniform circular motion formulas to see if I can figure it out. In this case, we can, which is great. We're going to use that centripetal acceleration equals v squared over r. And then we're also going to pull out the omega value of 2 radians per second to get the v. So and the radius from the equation, the a, right, to get r. So I know that my omega is 2 and my r is 1.5, because remember that a is always the radius of if it's uniform circular motion. I'm going to use this first equation to get my linear speed of 3, and then plug it into my centripetal acceleration to get 6 meters per second squared. And we'll also note that all of these practice problems come from old. Most of them are physics C exams. Every once in a while, I'll pull one from like an older physics. There used to be a physics B. So as we're doing this, if you're getting them right, you should be feeling really good right now. And if you're not getting them right, you know what you need to work on in the next couple of weeks, and that's okay too, right? That's why we're here. So I know there was some chatter in the chat about practice problems. Definitely, Kristen's awesome and is pointing you in a great direction. Some of the problems that she's pointing out are actually problems that I'm also pulling from. So you might get some repeats, which is good. It means that you're practicing, which is good. Okay, off my soapbox, talking about period and frequency. So period and frequency are new ideas for simple harmonic motion. Definition of period, we symbolize it with a capital T, and it's period is a time. So I think capital T like time. It's time for one cycle or complete revolution to occur. We measure it in seconds. So in simple harmonic, or in uniform circular motion, it's the time for the particle to go one time around the circle. If it's a pendulum, it's the time to go there and back. If it's mass on a spring, same deal, time to go there and back. If we look at it in terms of the actual wave function, you can see you kind of go up, you go down, and then when you're about to go up again, that's the end of the cycle. Frequency is the inverse of period, and it's the number of cycles or revolutions per second. So it's just one, the period is equal to 1 over the frequency. So it's going to be, your unit is going to be 1 over seconds. We give that a special name. We call it Hertz, HZ, which is something you probably have seen on like light bulbs and stuff. So that's the deal with period and frequency. We can talk about it in all of the different types of simple harmonic motion. And the general formula for it is in this box. This is on your equation sheet. The period is equal to 2 pi over the angular frequency, which is equal to 1 over the regular frequency. So let's do an example. So I'll get you started on this one, and then I'm going to open up another poll so that way we're practicing. We've got an equation of motion, tells you it's a simple harmonic oscillator, and it tells you that the equation is the second derivative of x with respect to t equals -9x. X is displacement, t is time. The period of and you're looking for the period of oscillation. So if we look backwards for a second here, we see that the period is equal to 2 pi over the angular frequency. So the first thing that you'll want to do here is think about where in this equation do we find the angular frequency, and then pull it out, get a number for it, and then plug it in to find the period. So I'll give you a second to do that. You're going to need to remember that general equation that we talked about at the very beginning. And if you would like to take a vote, poll is open. We'll give you maybe 45 seconds for this one. Okay, take another couple seconds. Okay, if you're going to vote, last chance. Great. Wonderful. Go team. So let's talk about it just because we weren't unanimous. And it's, it's good to hear it. So the correct answer here is D, and here is how we figured it out. So we're going to use the general equation that we talked about at the very beginning of this whole section. That's the thing that you need to memorize. So the first thing we'll do is take the equation or the function that they gave you to describe the simple harmonic oscillator and rearrange it so that way it matches that general equation. So all I did is I added the 9x over and it made it equal 0. From there, I said, okay, so I need to, in order to find my period, I know that I need to use 2 pi over the angular frequency. So I need to find out what the angular frequency is. The formula, the general formula says that the angular frequency squared is in front of the x. So I know that 9 is the angular frequency squared. So then to find the angular frequency by itself, I just take the square root, and the square root of 9 is 3. And so from there, I just plugged into my period formula to get 2 pi over 3 and my answer of D. So if you, looks like someone did 2 pi over 9, all we did is we probably forgot that it was squared, right? Which is no big deal. That's why we have to just kind of pay attention and make sure that we take that square root first. It's kind of a weird thing, that, like the angular frequency squared is kind of weird. So just remembering to get it by itself before we answer. Great. Okay, so second section here is mass on a spring. So we are going to talk about a couple of concepts that you've learned in other units before, but just like some special extra things that go with mass on a spring. So we'll also talk about period and frequency, specifically with mass on a spring, and then some possible spring setups super quickly. That's probably not really going to be too much on the test, but I want to at least show it to you in case there's a question about it. So first, mass on a spring, let's just like kind of unpack it a little bit. Here's what it looks like, right? It could be in this direction. It also could be horizontally. And we can see that as it oscillates, it makes this wave, right? It makes the sine and the cosine function. This is the same deal as we talked about before. Amplitude is the max displacement from the equilibrium position. So in this case, the spring is going to kind of hang, there's a spot where the spring would naturally, if it wasn't getting stretched or compressed, would just kind of just be chilling. That we give a special name. We call it the equilibrium position. And then if you want it to oscillate, you have to either like compress it or you need to stretch it, and then it will go back and forth. The amplitude is going to be the furthest point away from the equilibrium position. And then the angular frequency for this is going to relate to the spring constant. So reminder that the spring constant is basically just like how stretchy the spring is. Something like a mattress spring would have a big numbered spring constant, something like a slinky. If you know what a slinky is, it's like that toy that you can, it would go down the stairs by itself. It's very easy to stretch. It's a spring that's very easy to stretch that would have a smaller spring constant. Angular frequency also relates to the mass of the object. So there's a special formula for mass on a spring to calculate the period. It is on your equation sheet, which is nice. And it looks like this. So the period is going to be equal to 2 pi times the square root of the mass of the object over the spring constant of the spring. Now the period is also still definitely equal to 2 pi over the angular frequency. So all of that is still legit. There's just this extra way to calculate it for mass on the spring. Cool. And then you can see down here, all I wrote was that for this, the equilibrium position is your amplitude, or the max displacement from your equilibrium position acts as your amplitude, acts like your radius for uniform circular motion. So same kind of deal, just different, because it's a different motion. We have to just make a kind of like figure out which thing is which for mass on a spring. So here's another practice for you. It says an ideal massless spring fixed to the wall, shown above. Block of mass m is attached to the other end of the spring. It oscillates with amplitude a on a frictionless horizontal surface. The maximum speed of the block is v sub m. The force constant on the spring is. So take a second and see what you can do with this. This one is a little trickier, but we'll see what you can do. And then we'll talk about it. So let me open this up. take a minute or so on this one. Okay, if you're gonna vote, take a vote. Another 5 seconds or so. All right. So again, overall, really good, y'all. Go team. You guys are so, you're gonna be so ready. It's gonna be so great. Let's take a look at it. So in order to figure this out, first we have to pull out what we know, right? So we know the mass is m, we know the amplitude's a, we know that the max velocity is going to be v sub m, and we're looking for the force constant. So we're looking for k, right? So in order to figure that out, spring constant and force constant are force constant of the spring. Those are equivalent words. I should have said that. So to figure it out, we are going to use that equation for the period of a mass on a spring, and we're going to solve for k. You can see here that what I also did in order to kind of incorporate that velocity here and get it in terms of what they're asking for, I also used the 2 pi over the angular frequency, and did my little trick where we plug in the v equals angular frequency times r to get an answer. So set them equal to each other, do a little bit of algebra to rearrange, and then get an answer, which should be D. Okay. Great. So let's talk more about force. So when we've got something moving in simple harmonic motion in this way with this mass on a spring, the spring is going to cause something called a restoring force on the block. That's what makes it oscillate. So you can see here that the restoring force is going to point opposite the direction of the motion, right? So as the block is going left, the restoring force points right. And as the block is going to the right, once it passes that equilibrium position, it's going to point in the other direction. It's really just trying to pull it back towards the equilibrium position. And you see there's an equation here. This is also in your equation sheet for the restoring force of a spring. And it's going to be equal to negative the spring constant, and then the times the distance the spring is stretched or compressed. Anytime you see force in oscillations, I just want to say that Newton's second law is still totally helpful, and you're going to still use it all the time. So Newton's second law is still your go-to. As soon as you see forces, you should be definitely thinking Newton's second law. But there's just kind of this extra formula to calculate the restoring force for a mass on a spring. Same message here with energy. There's just like this extra thing. Conservation of energy is still 1,000,000% true, assuming there's no friction or any sort of thing pulling energy out of the system. There's just an extra formula. So we've got this potential energy of a spring, elastic potential energy is what I call it with my students. And it's going to be equal to 1/2 times the spring constant times that distance stretched or compressed squared. And if we look at this graph here, I love this graph because it's telling you that, as you're going through one one motion cycle. The type of energy that's happening for a mass on a spring is changing, right? When the mass on the spring is stretched to its max displacement, to its amplitude, then the potential energy, or the elastic potential energy is going to be at a max. As the spring is going through its equilibrium position and the spring isn't stretched out, the x is 0. There's no potential energy, but the block is going as fast as it will go. So there's a lot of kinetic energy. So the type of energy will change. It will go from potential to kinetic to potential to kinetic, but the total energy to calculate it will always be the same. And the easiest way to calculate your total energy is to stick in your amplitude for your x, because we know at the max displacement point, all of that energy is potential and the block is going to stop. So there's no kinetic energy. So I love this graph because it kind of just visually reinforces that the different types of energy is changing, but the total, this top kind of greenish line, will always be the same. Okay, so here we go. Potential energy of a particle constrained to move along the x-axis can be described by the function u of x equals 1/2 kx squared minus alpha times x, where both k and alpha are positive constants. Stable equilibrium points about which the particle oscillates are located at. So for this, I purposely put this one in here because you're going to have to use some potential energy knowledge that I didn't directly talk about, but is still totally legit, because in order to find a stable equilibrium point, what we're looking for is a spot where the force acting on the block is going to be 0. So thinking about how we can relate potential energy to force, there's a pretty important relationship that we need to, this is one of those things that we need to memorize because it's not on the equation sheet. There's a pretty important relationship between potential energy and force, and you're going to need it to figure out this one. So that's all the hints I'm going to give you for this one. I'll give you a minute to look at it and see what you come up with. I'll open up a poll. And yeah, just remember that we can relate potential energy and force to each other and see what you get. Take another 20 seconds or so. All right, last chance. If you're going to vote, now's the time. Okay, we were pretty split on this one, so let's take a look. That word stable equilibrium points definitely can throw folks off, so I want to make sure that we talk about it. So we know that we need to find the equilibrium points for this motion, and we've got an equation for the potential energy. We've got a function for the potential energy, right? So to find an equilibrium point, we have to know that at the equilibrium point, the restoring force of the spring is 0. That's going to be the key. The other thing we have to remember is that we can relate force and potential energy with this relationship, right? The force is equal to the negative derivative of the potential energy function with respect to x. If this is something that we either forgot or just like are unfamiliar with, definitely go back and watch the energy cram, but then also make sure we do some practice with this, because that's something that comes up on the test all the time. So, and it's not on your equation sheet, but it's an important relationship. So just like knowing we can relate force and potential energy by taking that negative derivative is going to be important. From there, to actually solve it, we're just going to take the derivative of this potential energy function, make it negative. Once we do that, we know that to find the equilibrium position, the force has got to be 0. So I'm going to say 0 equals my derivative, and then I solved for x. So our answer is B here. Okay, so let's use this one now. So which of the following is a differential equation that correctly describes Newton's second law for a simple harmonic oscillator of mass m and restoring force constant k? So I am only going to give you 30 seconds for this, because this is, I don't want you to overthink this one. This one's a pretty straightforward one. It tells you that you're using Newton's second law. Pulls open, tells you you're using Newton's second law. It tells you to use the restoring force. Take another 10 seconds here. Don't overthink it. Great. Okay, so overall pretty good. Again, correct answer here is B. 80% of you got it, which is great. Let's take a look just for those that need it. So we know that we need to use Newton's second law, right? So we're going to use F equals ma. And we know that in a simple harmonic oscillator, the force that's causing it to oscillate is the restoring force. And it's going to be equal to negative k times x. So all I did is I plugged in negative kx for my force in Newton's second law. And then the test was just like a little annoying and didn't write a. They wrote d squared x over, or the second derivative of x with respect to t for your acceleration. So that's kind of like, for me, that's just like a little eye rolly, but that is the correct answer. It should be B. Okay, and this is the really like last couple things here with mass on a spring. So you can see here, and I won't go too far into it because you can definitely come back and pause the video here or watch or look at the slides, but you can set them up horizontally or vertically. The only difference is when you set it up vertically, you have to figure out where the spring's new kind of like the new equilibrium point is, because gravity's involved now, right? Because if you put a mass on it, it's going to pull the spring down, but it will still resettle in a new equilibrium point. And then from there, you treat it the same way. It's just if you see something talking about like you attach the mass and then it falls, that's why. We're going to keep moving here just a little bit just to make sure that we have time. Let me see. Yeah, let's skip this one. It's here for you. This is what I was talking about. If once you let it go, it moves down to the equilibrium point. And then this one. Great. So I want to talk through, just because we haven't done any free response yet. So I want to take a minute and talk through that. And we've only got 15 minutes left. So this sort of simple harmonic motion comes up in free response not infrequently. So I want to just take a look and unpack a little bit. So this is coming from the 2012 practice exam that's been released. And here is what we have. So we've got this blocked mass is 0.3 kilograms placed on a frictionless table. And it's a horizontal spring. So it's an oscillator. It's a horizontal spring, mass on a spring oscillator. And we've got this velocity time graph that they give us here. So the first thing, it says determine an equation for v of t, including numerical values for all constants. So as soon as we see simple harmonic motion, I've got a velocity time graph, I know that I can pull things like the period out of the velocity time graph in order to figure it out. So we know we have the graph. We know that the period is one full motion. So if I take a look at this graph, here's how we figure it out. We start at wherever it starts, and then we go and we do one complete wave. And when we do that, we end here before it starts to go down again, right before it repeats. And so this is 0.7. So our period for this motion is going to be 0.7 seconds. And then it tells you your max velocity. And that's just going to be your amplitude, right? So I kind of eyeballed it and said 0.15 here for my max amplitude. From there, I wrote my general velocity equation for simple harmonic motion. Remember, you can get that by taking the derivative of that cosine equation we've been looking at. And then I just plugged in my amplitude, and I found my angular frequency using my period to find my omega, and got an answer here. You can see, I always like to just put these in here because there's like the amount of just like, you can get 1 point for just pulling the period off of the graph and saying that the period is 0.7 seconds. You can get 1 point for just using the correct equation and getting the angular frequency. You get 1 point for using the max speed for pulling out the amplitude from the graph, right? So I always include these because, you know, it's not like you have to get it completely right every time. It's not all or nothing, right? So just write down the equations that you think you want to use, and pull everything that you can from the problem, even if you can't get fully to an answer, because you can get a good amount of points just by putting in some of the pieces. So B says the equilibrium position at x equals 0. The equilibrium position is at x equals 0. Determine x of t. So from here, that makes it super easy, because if we know the equilibrium position is at 0, then if we get our max velocity here, we can solve for our radius. And remember that in simple harmonic motion, the radius and the max displacement and the amplitude are all just the same thing, right? It's just depending on the type of motion. So all of those equations always work, and we get an answer. Finally, it says calculate the value of K. So we're looking for the spring constant here. And again, I'm going to use my period relationship to figure that out. So I know my mass, I know my period from the graph, and I can just solve for K. So here, as I'm approaching that one, I'm like, okay, I know it's a mass on a spring. I know I need to solve for K. What formulas go with mass on a spring that also have K in it? And you're like, okay, well, there's kind of a lot, right? Because there's the restoring force, there's the potential energy function, and there's this period one. But hopefully we're looking at them and we're like, okay, well, what else do I know? I know my period from the graph, and I know my mass. So this is the relationship I'm going to use. And that's the scoring guidelines. You can see there's a lot of ways you can get that one. Okay, so the other two setups that we can see here, you can have two springs in series. You can also have two springs in parallel, and that's how they look. There's rules for how to get them, and we could derive it, but I'm not going to spend the time. Again, this is not, you're probably not going to see this, but if you do, I would say it's probably makes more sense for you to kind of think about how you're going to derive it than just to memorize this. But alternatively, if it's easier for you to memorize, just do it. If you've got something in series, you're going to do 1 over the effective spring constant of both of them together. That's what that is. It's going to be equal to 1 over the first spring constant of the first spring plus 1 over the second spring constant of the second spring plus however many springs you have. And then the last one, if you're in parallel, all we have to do is add up the spring constants. Because if we think about the forces pulling each of the springs separately, right? So we have to add them up. So this is here for you if you want it. Again, I'm not going to spend more time on it because I don't really think you're going to see too much of it on the test. Let's talk about pendulums. So this is the last type of simple harmonic motion, and it's perfect. We've got 10 minutes left. Let's talk about period and frequency in pendulums, and then quickly go through a derivation for a physical pendulum, just in case. So just like simple harmonic, or just like mass on a spring, pendulums have their own period equation. And the two things that affect the period of a pendulum are the length of the string of the pendulum and the acceleration due to gravity. So you'll see sometimes some questions, and there's one in here about like, what happens if you take a pendulum not on Earth? You go to the moon, or you go to Mars, or whatever. It will affect the period of a pendulum because your acceleration due to gravity will be different. It will not affect a mass spring oscillator because you know that these letters are different for mass spring oscillators, right? It's M over K versus L over G. There is something called the small angle approximation, which all the pendulums that you'll see on the test are going to do. Basically, it just says that assuming that we don't pull that pendulum too big of an angle, I think it's like 20 degrees maybe, they are going to have the same period regardless of how far of an angle you release them from. There's a derivation for how to get it here. If you care, the thing that really matters about this is just that remembering that there's a component to the weight. That's the thing that's causing the pendulum to swing back and forth. It's the weight of whatever the bob on the end of the pendulum is, but it's not, the weight goes straight down, right? So it's not the weight itself, it's the component of the weight pointing back towards the center. Okay, so here's that example I was talking about. So a pendulum, a period of 1 second on Earth, acceleration due to gravity is g, is taken to another planet where the period is 2 seconds. Acceleration due to gravity on the other planet is most nearly. So I'm going to give you 30 seconds, and this will probably be the last one we'll do as a poll, just because of time. But if you want to take 30 seconds or so to see if we can get an answer for this one, and then I will talk about it. You're definitely going to want to use that period of a pendulum formula, so 2 pi square root L over G. Great, got some votes coming in. Okay, last chance if you're going to take a vote. I know this is quick. Just never have enough time, y'all. So much physics to do. Okay, so I think we got less votes this time, but for the people that did vote, crushed it. Everyone got it right. Good work. So to take a look at this real fast, all we would do is compare the period of the pendulum at G, and then when you change it to the other planet. So all I did is I solved the original equation for plugging in 1 second for G, and then I plugged in 2 seconds for G, and I just compared them to figure it out. You could alternatively plug in numbers for like the length and stuff, because that, if you can keep that the same and then just see what happens to G, that would be something that you could do too, either one. Okay, so let's just talk about this one. So frictionless pendulum, length 3 meters, swings with an amplitude of 10 degrees. At max displacement, the potential energy of the pendulum is 10 joules. What's the kinetic energy of the pendulum when its potential energy is 5 joules? So this one should be like crush it in the bank, because this is just straight conservation of energy. If we take a look, we know that at the max displacement, the pendulum's going to stop. So when that happens, all of the energy is potential energy. So this 10 joules of energy is the total energy in the system. There's no there's no, friction or a force that would take energy away. So we know that if the total energy is 10 joules, if the potential energy is 5 joules, then the kinetic energy also has to be 5 joules. So this is one of those where, like, hopefully, as we continue to do practice, you're looking at it and you're like, bam, took me 20 seconds to read it or whatever it is, takes me 21 seconds to answer it. That's hopefully where we can get to in the next few weeks. Okay, and then in the last 5 minutes, I'm going to do the fastest physical pendulum derivation you've ever seen. There is a standard on the AP Physics C list of all of them, all of the objectives, that says, derive the expression for the period of oscillation for various physical systems oscillating in simple harmonic motion. So how this is different than what we talked about before is that it's no longer just like a pendulum bob on a string. It's an actual object oscillating. So this is a rod that's attached at the end here that hopefully you can kind of picture it swinging back and forth. So I'm going to talk through how to do this quickly. Remember that you have these resources, so you can pause the video or you can go into my slides and unpack this as you need to, if you care. I don't think I don't know. Sometimes it comes up, so I wanted to at least cover it. It's not super, like, this is one of those things that's like, they might do it. Who knows? So I wanted you to be able to at least see it so that you know how to do it. So things that we know that theta is the angle with the vertical. We know the mass, we know the length, and it gives us, I know we didn't read it all, but it gives us the moment of inertia, rotational inertia about the pivot suspended from the bar. So we know the rotational inertia around the axis of rotation. So to figure out and answer a differential expression for the first one, we're going to use Newton's second law of rotation. We're going to use the relationship between mass and acceleration due to gravity and weight. We're going to remember that the angular acceleration is the second derivative of theta with respect to time. All sorts of stuff, right? And we're going to use our torque relationship. So Newton's second law here for rotation, plugging in our torque function or our torque formula to give me the moment of rotation of the bar times the angular acceleration. Then I'm going to plug in for my force here. So I didn't write theta, but this would be negative mg sine of theta, and it's crossed with the position, which is x. And then from here, all I did is plug in, because we're looking for the general formula for the simple harmonic motion. So we need this second derivative of something and then the actual angle itself. So we need this this angular acceleration to look like second derivative of theta with respect to time here. So that's how we would find just this differential equation for angle theta the bar makes with the vertical. We then apply the small angle approximation. All that means is we say instead of sine theta, we've got theta. And then we can go through and plug in and get an expression for the period of the motion using the constants that they gave us. So if we look here, all I did is I rearranged the formula that we got from part A, the equation we got from part A, so that way it looked like our general formula, so that way I could pull out my angular frequency squared. So remember that if we look at this looks like that general formula, pull out our angular frequency, plug it in to find our period, get an answer for our period. Okay, and then the last part says, describe an experimental procedure you would use to make additional membership needed to determine the rotational inertia of B. So here, again, you can go through it, but one way you could do it is measure the period. So let it oscillate 10 times and then divide by 10 to determine the period and then calculate IB using that. Basically, you could do a similar thing with a photo gate if you wanted to figure out IB. Last one, it asks how you would determine the center of mass of the bar. This harkens back to when we talked about center of mass. Easiest way would be to, like, it says put it on a fulcrum or near the edge of a table. Remember that the support has to be, you have to support the center of mass, otherwise it will start to rotate, because then there's torque. And so you could put it somehow, measure it so that it's balanced, and then above it would be the center of mass. So that's physical pendulums, and like I said, the fastest thing ever. General, just kind of wrapping up because it is 7 o'clock. You really, really, really should memorize that general formula for simple harmonic motion. And then really the other big takeaway specifically for simple harmonic motion is that all of the other physics that you already know and have been learning for, however long, applies to simple harmonic motion. So Newton's second law, energy conservation, relationship between velocity and acceleration and displacement, all of that still totally applies. There's just a few extra things to remember. So I know that's like not ideal, but just don't lose sight of the all of the really good physics that you already know, just because now it's oscillating. And because I think that feels scarier than it has to a lot of times. And then, I always say, list what you know, what you're looking for. When in doubt, draw a diagram. And then if you get freaked out, take a deep breath, because you've been studying and you're here and you can do it. And that's it. So next cram, last unit for mechanics is going to be Unit 7, gravitation. We'll do it next Tuesday, the 20th at 8 Eastern. We definitely invite you to trivia tomorrow. It's at 9 Eastern. And it's on the stuff we were talking about today. So a lot of the problems hopefully will reflect what we were doing today in this cram. Kristen is going to hop over to Discord if you want to chat more. You guys did a great job in the chat today. I was kind of watching it, but also not completely. So talk to Kristen. I'm going to go through and just, read all of the awesome things that you've already said. And I'll stick around for just a moment in case there's any last questions on the in the chat. But otherwise, head to Discord. Kristen is there. She can help. She's an all-star. And I'll be around too. So thank you so much for listening. Have a great rest of your night. And good luck. You can do it.